We now look at some simulation results of a reduced order model that's based on the full order model of lithium deposition on overcharge. I'm not going to take the time to develop all of the reduced order model equations because, as I mentioned in the previous section, we're not entirely satisfied with the reduced order model the way it stands right now, and we think that we have a way to improve it. So rather than dwell an awful lot of time on something that's probably not going to be ultimately valuable, I do want to spend some time at least looking at the results, the type of results that you get out of a reduced order model, because ultimately in this chapter we're going to be developing some controls ideas that use these models. So I want you to see results that come out of reduced order models, even if they're not the final reduced order models that you might end up using. When we are comparing the simulations of the reduced order models to see how good they are, we compare them to the PDE model because we are assuming that the PDE model is correct. We're assuming that that is exact. So if we can match the PDE model accurately with a reduced order model, we're doing well, is our assumption. So question is, how well does our approximation of the average side reaction flux match the exact calculation of the average side reaction flux over the electrode? And we're going to compare both of those results. We did a lot of simulations again. In each simulation, the scenario was very similar to what we did for the SEI model. So the cell was initially at rest, and we applied a sudden pulse of current, and the resulting side reaction average flux from the PDE model averaged over a 1-second interval as compared to the same result from the reduced order model. We used COMSOL again, using MATLAB as the method to automate doing many simulations in COMSOL. And our reduced order model was coded in just straight MATLAB code. In each simulation, we simulated 1.2 seconds of real time. So the first 0.2 seconds was a rest interval that allowed COMSOL to stabilize its initial solution, and then we applied a pulse of current and we monitored what happened over the next 1 second, so up to time 1.2 total, and this is 0.2 there. So very similar to what we did for the SEI, slightly different numbers, but there's no real reason for the different numbers, it's just the way we happen to do it. The cell parameters that we used in the simulation are listed in the appendix to this chapter. They match the ones used by Aurora in the original paper on lithium deposition. The applied current to the cell was varied between 0C and 3C in increments of C over 33, and the initial cell state of charge was varied between 0% and 100% in steps of 1%. Temperature was held constant at 25 degrees. The reduced order model, I mentioned I'm not going to develop it here, but one thing that makes it just a little bit less satisfying than it could be is that it has a tuning factor. It has a value of beta built in. And we tune this value until we get reduced order model simulations that seem to match pretty well the PDE simulations. There's no way that we figured out to automatically compute this number, though. We found out that for these simulations, beta equals 1.7 worked fairly well. And it roughly implies that as I apply a charge pulse, the electrolyte concentration near the separator changes nearly twice as quickly as it does near the current collector, is roughly what that beta factor means. Ran a lot of simulations, 10,100 simulations. And as one point of comparison, the full order PDE simulations took about 12 hours to complete using 3 cores on an Intel i7 processor using COMSOL, compiled product. The reduced order model simulations took 21 seconds to complete using an average of 1 core running MATLAB and interpreted product on the same machine. So the speed up of this reduced order model is about 5,000 to 1. And again, that's why we want to use a reduced order model, is that we can greatly reduce the computational requirements of a battery management system if we have a good reduced order model instead of trying to simulate a PDE kind of model. Looking at the results, remember that lithium plating occurs anywhere the side reaction overpotential is negative. So if we plot, for example, a snapshot like we do here of what happens when we start at 90% SOC and we apply a 2C pulse and we look at the results, the solid line shows the overpotential versus anode location of the PDE, and the dotted line is the same result for the reduced order model. And remember that 0 is the critical point. So the the full order model says lithium plating happens between about, I guess we have it here, 42 microns and 85 microns, the width of the anode. And the reduced order model says instead that lithium plating happens between about 49 microns and 85 microns. So they're similar, but they're not exactly the same. The reduced order model overpredicts lithium plating for most of that distance because the overpotential is smaller in a signed sense compared to the PDE model. So even though it's over a shorter distance, shorter length, there's more of it, and overall there is an overprediction of lithium plating in this example. And looking at then at the total amount of side reaction current versus time for that exact same example, so at time negative 0.2, I guess you could say this first 0.2 seconds is the equilibrium, putting the COMSOL model into equilibrium, and then we apply the pulse at time 0. You can see that the PDE quickly jumps to some side reaction current density, and the reduced order model immediately jumps to an even bigger negative side reaction current density, so it's over predicting the side reaction that's happening. The PDE evolves a little bit over time. The reduced order model, similar to our SEI model, does not evolve over time and stays constant. So we're getting similar results, but not nearly as close. Relatively speaking, it's about maybe 15 or so, 20% relative error in this case, which is quite a lot higher than it was before. Qualitatively, though, looking at the figures on the left, we have instantaneous degradation rate of the PDE model versus current and SOC, and on the right, the reduced order model versus SOC and current. And looking at the scales, they're very, very similar, very, very similar shape. So we're getting a great deal of the model, but maybe not perfect fidelity of the PDE model using this reduced order mechanism. Deposition is worse at high SOC and high charge rates, very similar in nature to SEI, except far worse in magnitude. And there's, like I said, general agreement, but greatest mismatch at high charge rates. Like we did before, I'm showing some cross-section plots here of that 3D plot so we can compare the PDE to the ROM. And with the SEI model, the dashed lines and the solid lines were so close we couldn't tell them apart. Here they're not so close. So the red goes with red, green with green, blue with blue, etc. So you can see which are the corresponding results, and so they're similar, but they're not exactly aligned, or they're not aligned as well as they were for the SEI model. So it's a decent, maybe, first attempt at an overcharge model, but it still leaves some room for improvement. This plot here is most telling. This is probably the most important set of plots for this particular mechanism. And the one on the right is nice and colorful. I don't know if it's quite as helpful as the one on the left, but on the right it's showing the modeling error between the partial differential equation model and the reduced order model. And red means I've got the biggest relative error, and blue means that I've got either no or very little error. Going to the plot on the left that's not colored, there's 3 regions that are drawn with lines in between. In this region, neither the PDE model nor the reduced order model predict overcharge. In this region, both of them predict overcharge. And in the middle region, there's a disagreement, and the ROM predicts overcharge, but the PDE does not. So in this case, the reduced order model is being a little bit more conservative in that it's predicting overcharge whenever the PDE model predicts overcharge, and some other times as well. And that's exactly what we want for a control scenario. We want to be able to control this cell right up to the point of overcharge, but no further than that. And it's best if we are slightly conservative into where we think that the lithium plating happens, so that I don't overconfidently charge a cell when I shouldn't. A standard type of a charging protocol for a single cell nowadays says something like this. It says charge at maybe a 1C rate, and the SOC would keep on going up until you hit a voltage limit, and then at that voltage limit you take a constant voltage, which might do something like this. Now you can see, based on this picture, what that terminal voltage limit is trying to do. It's trying to avoid this lithium plating. I don't want to go above some line where I'm going to cause dramatic fast capacity loss. But based on this figure here, we can also see that that charging profile, while it might be safe, is nowhere near optimal in terms of how quickly I can charge a cell. If I'm worried about fast charging, if I knew the truth, if I knew the actual PDE model, the fastest I could charge a cell would be to follow this contour here. So I would start out with a faster than 3C charge rate until I hit this state of charge, and then I would follow that contour all the way up to the top. Well, using this particular reduced order model, what we would do instead is we would follow this contour up to the top, which is not quite as fast, but it's almost as fast, and both of them are far faster than doing something like that. The most important thing that the lithium deposition on overcharge model gives us is that dividing line, that boundary line, so that I can use a cell all the way up to that boundary line but no farther. So I can have a time optimal charger. And here we're saying that this reduced order model, while it has some flaws, is able to do that prediction pretty well. So that's basically what we've said there. And so we've talked about the time optimal charger based on the full order model, and based on the reduced order model, we'll have somewhat slower charging, but still much better than just using a standard constant current, constant voltage kind of charging methodology. We did some more simulations that were not just simple pulses, but longer length simulations to see what happens if delta t is different. And can the charge pulse, how long can this charge pulse length be before the full order PDE model and the reduced order model results are quite different? And in our experiments, we found that for this reduced order model, the pulse lengths had to be less than about 10 seconds long for the model to work well, and pulse lengths greater than 10 seconds in duration had significant error, significant mismatch between the PDE and the reduced order model. The reason is this quasi-static nature of assumption 1, saying the cell is resting and then I apply a pulse, is violated by a long duration pulse. And then the phi e that is part of the overpotential in phi s minus phi e, etc., gets a significant offset over time versus its kind of static version. And that moves this crossover point. And when that crossover point moves, remember the phi s, the overpotential looks like that. And if I change something so it moves like that instead, I'm integrating the loss of lithium over a larger region in the electrode. And then the reduced order model begins to underpredict the value of lithium plating. So that's not very good. So because of that, this particular reduced order model we propose has greatest value for computing current limits in some dynamic applications, such as a hybrid electric vehicle type of application, where we can't develop a long-term bias in the electrolyte potential due to a long current pulse or power pulse. We make another comment before concluding this section regarding efficiency. The speed up of the reduced order model versus the PDE can be much greater than 5,000 to 1 if I pre-compute some model solutions and store them in a table. Then computing any value is nearly instantaneous using a table lookup. So it's possible to employ more sneakiness and more memory to reduce the computation requirements. However, the model solution in this case does change as the film resistance changes. It did not change, if you remember, for the SEI model, but for this one it does. So this lookup table would have to be recomputed periodically as the film resistance changed over time. So maybe once per operational period, maybe when I shut down the vehicle, I recompute the table for next time I use the vehicle, and so forth. Overall, it's an interesting model. It can perform well in some situations, but it has some limitations that we're working on, and we think we probably have a solution for, but we haven't yet published those results. We've looked at two reduced order models. There's other degradation mechanisms possible. There's cathode material loss due to dissolution of the cathode into the electrolyte. There's stresses and strains and things like that you might look at, because maybe that's going to cause fracture of the active particles or breakup of the electrode matrix or any number of things. There's a lot of possible models that could be developed over time. Here I've shown you only one in detail and one with a small amount of detail to give an idea that we can do reduced order models of these degradation mechanisms too. I don't want to dwell on that any further. At this point, I do want to spend the rest of this course, just a few more sections, saying what can we do with these degradation models that's of any value inside a vehicle application, because there's some pretty cool stuff, and I think that's where the future lies.